The isolated brown dwarf has shown indications of potential aurorae, as discovered by NASA's Webb. Greetings and salutations to everyone. In today's video, we will be discussing a fascinating discovery made by NASA's James Webb Space Telescope. They have identified a brown dwarf called W1935 that exhibits infrared emission from methane in its upper atmosphere. What makes this discovery even more intriguing is the fact that the brown dwarf is cold and does not have a host star, leaving scientists puzzled about the source of the energy in its upper atmosphere. The research team has put forth the hypothesis that the methane emission could be a result of processes generating aurorae. They also suggest that internal mechanisms or interactions with interstellar plasma or a nearby active moon could potentially explain this emission. Without further delay, let's dive into our discussion on this captivating topic. The James Webb Space Telescope, operated by NASA, has enabled astronomers to detect a brown dwarf, a celestial object larger than Jupiter yet smaller than a star. Surprisingly, this brown dwarf, named W1935, exhibits infrared emission from methane in its upper atmosphere, despite its cold nature and lack of a host star. The absence of an apparent energy source for the upper atmosphere has puzzled scientists. As a result, the research team hypothesizes that the emission of methane could be attributed to the occurrence of aurorae caused by various processes. The presentation of these discoveries is taking place at the 243rd gathering of the American Astronomical Society in the city of New Orleans. In order to shed light on the enigma surrounding the infrared radiation emitted by methane, the researchers sought inspiration from our very own solar system. They discovered that methane emission is a prevalent characteristic of massive gas planets such as Jupiter and Saturn. The source of this emission is attributed to the heating of the upper atmosphere, which is intricately connected to the occurrence of aurorae. The captivating phenomenon of aurorae on Earth occurs when the sun's energetic particles are ensnared by our planet's magnetic field after being propelled into space. These particles gracefully descend along magnetic field lines near the poles, gracefully colliding with gas molecules and giving rise to enchanting undulating displays of light. Jupiter and Saturn exhibit comparable processes that generate their own aurorae, which involve interactions with the solar wind. However, these awe-inspiring celestial bodies also receive contributions to their aurorae from the presence of active moons in close proximity, such as Io for Jupiter and Enceladus for Saturn. The absence of a stellar wind, which typically contributes to the auroral process and provides the necessary energy for methane emission in the upper atmosphere, presents a perplexing enigma for isolated brown dwarfs like W1935. To shed light on this mystery, the team postulates that internal processes akin to the atmospheric phenomena observed on Jupiter and Saturn, or external interactions with interstellar plasma or a neighboring active moon, may offer potential explanations for the emission. The discovery of these aurorae unfolded like a captivating detective story, with Jackie Faherty, an astronomer at the American Museum of Natural History in New York, leading a team granted time with the Webb telescope to investigate 12 frigid brown dwarfs. Among these celestial objects were W1935, unearthed by citizen scientist Dan Caseldon through the Backyard World's Zooniverse project, and W2220, discovered using NASA's Wide Field Infrared Survey Explorer. Webb's meticulous observations unveiled striking similarities in composition between W1935 and W2220, rendering them virtual duplicates of one another. Both W1935 and W2220 exhibited comparable levels of brightness, temperatures, and spectral characteristics associated with water, ammonia, carbon monoxide, and carbon dioxide. However, there was a notable divergence in their methane emissions. Unlike the expected absorption feature observed in W2220, W1935 displayed distinct emission of methane at a specific infrared wavelength that aligns perfectly with the unique sensitivity of the Webb instrument. Faherty expressed surprise at the unexpected emission of methane from the brown dwarfs, as they had anticipated its presence based on previous observations. However, rather than absorbing light, the methane was actually glowing. This discovery left Flaherty puzzled, questioning the reason behind this phenomenon. Using computer models, the team made inferences about the cause of the emission. The models revealed that W2220 followed the expected pattern of energy distribution, with decreasing temperatures as altitude increased. However, W1935 yielded unexpected results. The most accurate model indicated a temperature inversion, where the atmosphere actually became warmer at higher altitudes. The presence of this temperature inversion is truly perplexing, commented Ben Birmingham, the lead modeler from the University of Hertfordshire in England. While we have observed similar phenomena in planets with nearby stars that provide heat to the stratosphere, witnessing it in an object without an obvious external heat source is remarkable. To find some clues, the team turned their attention to our own solar system and examined the gas giant planets. These planets can offer insights into what might be happening in the atmosphere of W1935, located over 40 light-years away. In the realm of planets such as Jupiter and Saturn, the team has come to the realization that temperature inversions play a significant role. Although the causes of stratospheric heating are still being investigated, prevailing theories within the solar system suggest that external heating from aurorae and internal energy transport from deeper layers of the atmosphere are the primary factors, with the former being the leading hypothesis. It is worth noting that the utilization of aurorae to explain observations of brown dwarfs is not unprecedented. Astronomers have previously detected radio emissions emanating from several warmer brown dwarfs and attributed them to aurorae. In an effort to gain further insights into this phenomenon, searches were conducted using ground-based telescopes like the Keck Observatory to identify infrared signatures from these radio-emitting brown dwarfs. However, the results of these searches were inconclusive. The inaugural auroral contender to exist beyond our solar system, known as W1935, displays the distinct hallmark of methane emission. Notably, W1935 holds the title for the frigid auroral contender situated farthest from our solar system, boasting an effective temperature of roughly 400 degrees Fahrenheit, 200 degrees Celsius. This temperature stands approximately 600 degrees Fahrenheit higher than that of Jupiter. The solar wind, a significant factor in the occurrence of auroras within our solar system, is influenced by active moons such as Io and Enceladus, which impact the auroral processes of Jupiter and Saturn respectively. However, W1935, lacking a companion star, does not have the presence of a stellar wind to contribute to this phenomenon. It remains uncertain whether an active moon could potentially influence the emission of methane on W1935. According to Flaherty, the discovery of W1935 provides a remarkable expansion of a solar system occurrence that cannot be attributed to the influence of star radiation. With the utilization of the Webb telescope, scientists will have the opportunity to thoroughly examine the chemical aspects and explore the potential similarities or distinctions in the auroral processes that exist beyond our own solar system. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.